Hello my dear students. Now I would like to solve some more problems on this topic. The next question is ionization energy of hydrogen like ion. Ionization energy. This is ionization energy. Ionization energy means the energy required to remove the electron from its outermost orbit. Ionization energy of a hydrogen like ion A is greater than that of another hydrogen like ion B. Here hydrogen like ion A is greater than the hydrogen like ion B. If R is the radius of the orbit, U is the speed of the electron, it is speed, U is the speed of the electron, and E is the energy of the atom, E is the energy of the atom, and L is the angular momentum of the electron respectively in the ground state. Here the ionization energy of a hydrogen like ion A is greater than that of another hydrogen like ion B if R, U, E and L represents the radius of the orbit. Then electron respectively in the ground state. But in this ground state R, the option A is RA is here, the option A is RA is greater than RB. No, this is wrong. And the option B is UA is greater than UB. Yes, here UA is greater than UB because the speed of the electron of the hydrogen like ion A is greater than B and EA is greater than EB. No, this is also wrong. The angular momentum of the electron A is greater than B. This is also wrong. Here in this case UA is greater than UB. The option B is the right answer. And the next question is doubly ionized helium atom and hydrogen ions are accelerated from rest through the same potential difference. The ratio of final velocities of helium and hydrogen is when the doubly ionized helium atom and hydrogen ions are accelerated. When these ions are accelerated through the certain velocity, now I can write this equation, that is Q into V, accelerated through a potential difference. QV is equal to, here that QV is equal to the kinetic energy half mv square. But the ratio of the final velocity, that is V is equal to root of 2Q into V divided by m. In this formula, the V is proportional, directly proportional to Q and inversely proportional to m. The ratio of final velocities of helium and hydrogen atom is the velocity of helium to the velocity of hydrogen atom is equal to, here the charge of the helium divided by charge of the hydrogen into mass of the hydrogen divided by mass of the helium, that is equal to root of charge of the helium, that is 2 times of its atomic number electron divided by charge of the hydrogen, that is E, 1.6 into 10 to the power of minus 19 into mass of the hydrogen is 1, mass of the helium is 4. Here this is 4m and this is only the mass of the hydrogen is m. You get the answer is 1 divided by root 2. 1 divided by root 2. Here the option A or option C. This is 1 divided by root 2. Option C is the right answer. Next question is the energy of a hydrogen atom in the ground state is minus 13.6 electron volt. The energy of a hydrogen atom in the ground state is minus 13.6 electron volt. The energy of a helium ion in the first excited state will be, we know the formula, energy in the nth orbit of an hydrogen atom, that is En is equal to minus Z square. Here En is equal to minus Z square into 13.6 minus Z square into 13.6 divided by N square electron volt for the first excited state of helium atom. For the first excited state of helium atom, here in this case N equal to 2 and Z equal to 2. First excited state, that is N equal to 2. For helium atom, Z equal to 2. And energy of a helium atom, energy of a helium atom in a first excited state, that is energy of a helium atom in a first excited state is equal to minus Z square. That is, here or you can write this equation. See, Z square means 4. Z equal to 2 square, that is 4 divided by 4 divided by N square, that is also 4. 4 divided by 4 into 13.6. Now you get the answer again, minus 13.6 electron volt. Minus 13.6 electron volt. Option A is the right answer. Next question is, out of the following which one is not possible energy for a photon to be emitted by a hydrogen atom according to Bohr's atomic model? Here you know the energy level diagram from using Bohr's atomic model. Energy level diagram, in this case N equal to 1, the energy in the ground state is minus 13.6 electron volt, and N equal to 2 minus 3.4 electron volt, minus 3.4 electron volt. Then N equal to 3, it is minus 1.51 or 1.51 electron volt. When N equal to 4, N equal to 4, the answer is 0.85. When N equal to 5, the answer is 0.58 electron volt. But when an electron jumps from second orbit to the first orbit, the energy is, that is 10.2 electron volt. From using the formula minus 13.6 divided by N square, N2 divided by N1, the answer is 10.2. But when an electron jumps from 3 to 1, here in this case the answer becomes 12.09 electron volt. When electron jumps from the first orbit to the, here N equal to 2 to N equal to 1, the answer is 10.2. The answer is 10.2. When an electron jumps from 3 to 1, the energy value is 12.09. But here the options are given. Option A 1.9 electron volt, option B 11.1 electron volt, option C 13.6 electron volt, option D 0.65 electron volt. Here 13.6 electron volt, it is in the ground state value, and N equal to 2, that value is minus 3.4. Here 0.65 and 1.9 value, these values are less than minus 3.4. Here the option B is the right answer. Out of these choices, 11.1 electron volt, it is not possible energy for a photon to be emitted hydrogen atom according to Bohr's atomic theory. And the next problem is, electron in hydrogen atom first jumps from third excited state to second excited state, and then from second excited state to the first excited state. Now I draw the energy level diagram. Here this, along this axis, this is y axis and this is x-axis. Here in this axis, this is n equal to 1, n equal to 2, and here n equal to 3. Electron in hydrogen atom first jumps from third excited state to the second excited state. Third excited state to the second excited state. Here this is case 1. And then from second excited state to the first excited state. This is case 2. The ratio of wavelength lambda 1 and lambda 2 in these two cases. For the first case, n1 equal to 3 and n2 equal to 2. Now 1 by lambda 1 equal to, or at infinity we don't have the value, 1 by 9 minus 1 by 4, 1 by n1 square minus 1 by n2 square. Here or infinity is equal, this is Rydberg constant. Now we get 1 by lambda 1 is equal to r into infinity, that is 4 minus 9 divided by 36. You get the answer minus 5 or infinity divided by 36. It is equivalent to lambda 1 is equal to minus 36 divided by 5 or into infinity. Like this. In the second case, electron jumps from second excited state to the first excited state. In this case, 1 by lambda 2 is equal to or infinity, and 1 by 4, second n1 equal to 2, n2 equal to 1, minus 1 by 1. In this case, we get the value minus 3 into or infinity divided by 4. Here lambda 2 is equal to minus 4 divided by 3 into or infinity. Now the ratio of their wavelengths lambda 1 by lambda 2 is equal to minus 36, 5 or minus 36, 5 or infinity into 3 or infinity divided by minus 4. We get the answer lambda 1 by lambda 2 is equal to 27 divided by 5. The ratio of wavelength lambda 1 and lambda 2 emitted in the two cases. In the first case, electron jumps from third excited to the first excited state. The wavelength in the first case is minus 36 divided by 5 into or infinity. Next problem is, a hydrogen atom in its ground state absorbs 10.2 electron volt of energy. The orbital angular momentum is increased by, and the electron after absorbing 10.2 electron volt of energy, goes to its first excited state. Here n equal to 2. In the first excited state, n equal to 2 from the ground state, that is from the ground state. In the ground state, n equal to 1. A hydrogen atom in the ground state absorbs 10.2 electron volt the energy. The orbital angular momentum is increased by increase in momentum. Yeah. The increase in momentum, the angular momentum is integral multiple of nh divided by 2π, or increase in momentum is equal to only h divided by 2π. You substitute the value, the Planck's constant value, that is 6.6 into 10 to the power of minus 34 divided by 6.28. You get the answer 1.05 into 10 to the power of minus 34 joule. Second option A is the right answer. The next question is, hydrogen atom is excited from ground state to another state. Hydrogen atom is excited from The hydrogen atom is excited from ground state. This is the ground state to another state. Suppose if I consider this is another state with the principal quantum number, that is principal quantum number n, that is equal to 4. Then the number of spectral lines in the emission spectra will be, the number of spectral lines in the emission spectra will be the possible number of spectral lines. Here we have the formula to calculate the possible number of spectral lines in the emission spectra. That formula is n into n minus 1 divided by 2. From using this formula we can calculate the possible number of the spectral lines for the given number. Here n equal to 4, n equal to 4, 4 into 4 is 4 into 4 minus 1 divided by 2, that is 4 into 3, 12, 12 by 2 is equal to 6. Option D is the right answer. And the next question is the wavelength of first spectral line in the Balmer series of hydrogen atom. The wavelength of the first spectral line in the Balmer series of hydrogen atom. This is the wavelength 6561 angstrom. Lambda is equal to 6561 into 10 to the power of minus 10 meter. The wavelength of the second spectral line in the Balmer series of singly ionized helium atom. We know that the simple formula. That is 1 by lambda is equal to r z square 1 divided by n1 square minus 1 divided by n2 square. This is the semi-empirical formula. In this formula, the wavelength of first spectral line in the Balmer series of hydrogen atom is 6561 angstrom. In this case, n2 is equal to 3. For this wavelength, this is 6561 angstrom. In this case, n2 is equal to 3 and n1 equal to 2, because this is Balmer series. For this series, we get 1 divided by 6561 is equal to r into 1 square for hydrogen atom, and 1 by 4 minus 1 by 9, you get the answer pi r divided by 36. This is question number 1. And for the second spectral line in the Balmer series of singly ionized helium atom, in that case you get the answer 1 by lambda is equal to r into 2 square for helium atom, r into 2 square into 1 divided by n1 is 4 and minus 2 square, 1 divided by 4 minus 1 divided by 16. This is equal to 3r divided by 4. This is equation number 2. In this case, n1 equal to 2 and n2 is equal to 4. From using these two values, you get 3r divided by 4. When you are dividing these two equations, it is lambda divided by 6561 is equal to 5r divided by 36 into 4 divided by 3r, that is equal to 5 divided by 27. Therefore, lambda is equal to 1215 angstrom. Lambda is equal to 1215 angstrom. Option A is the right answer. The next question is the extreme wavelengths of Fashion series are. The extreme wavelength. When I am going to calculate the extreme wavelength, we know that the formula, the maximum and minimum wavelength formula. 1 by lambda maximum for Fashion series is 1 divided by 3 square minus 1 divided by 4 square, and for minimum 1 divided by lambda minimum is equal to 1 divided by lambda minimum, that is r into 1 by 3 square minus 1 by infinity. Directly I can write here 9 divided by r, here r into 1 by 9 minus 1 by 16, 1 by 9 minus 1 by 16, we get the value 144 divided by 7 into r. It is also equal to 144 divided by 7 into 1.1 into 10 to the power of 7, or it is equal to 1.89 into 10 to the power of minus 6 meter, or it is 1.89 micrometer. This is micrometer, for this is maximum and this value is minimum. The minimum value is 9 divided by r, 9 divided by 1.1 into 10 to the power of 7 Rydberg constant. We get the answer 0.818 micrometer. Here the extreme wavelength of Pascal series or lies in between 0.81. Option B is the right answer. The next question is the wavelength of the first line of Lyman series. The wavelength of the first line of Lyman series for hydrogen atom is equal to that of the second line of the Balmer series of hydrogen like ion. The atomic number Z of hydrogen like ion is. In this problem, the wavelength of the first line of the Lyman series for hydrogen atom, that is 1 divided by lambda is equal to r into, for Lyman series, 1 by 1 square minus 1 divided by 2 square, and the wavelength of second line of the Balmer series, that is 1 divided by lambda dash is equal to z square into r divided by 1 minus 2 square minus 1 divided by 4 square. According to that question, lambda is equal to lambda dash. Lyman series of hydrogen atom is equal to second line of the Balmer series. Then I write this equation, lambda is equal to lambda dash. Therefore, r into 1 divided by 1 square minus 1 divided by 2 square is equal to 2 square is equal to z square into r divided by 1 by 2 square minus 1 divided by 4 square, or we get the value here 3 by 4 is equal to 3z square divided by 16, or z square is equal to 4 or z equal to 2. Option D is the right answer. The next question is the first line of the Lyman series in a hydrogen spectrum has a wavelength of 1210 angstrom. The corresponding line of a hydrogen like atom of Z equal to 1. Z equal to 1. In this case, or Z equal to 11, sorry, Z equal to 11 is equal to, by Bohr's formula or Balmer formula, 1 by lambda is equal to z square r into 1 divided by n1 square minus 1 divided by n2 square. For the first line of Lyman series, n1 equal to 1 and n2 is equal to 2. Now I write this equation, 1 by lambda is equal to z square r into 3 divided by 4. This is for first line of the Lyman series in hydrogen spectrum. And for hydrogen atom, Z equal to value is 11. This value is given in this problem. Now 1 by lambda dash is equal to 121 R. 1210. This is 1210 R into 3 divided by 4. This is 3 divided by 4. This value z square. 3 divided by 4. This is equal to lambda divided by lambda dash 3r divided by 4 into 4 divided by 1210. This is 1210 into 3. This value becomes 1 divided by 120, or lambda dash is equal to lambda divided by 121. Here 1210 divided by 128, you get the value is 10 angstrom. The option D is the right answer. The next question is, what is the ratio of the shortest wavelength of the Balmer series to the shortest wavelength of Lyman series? For a Balmer series, 1 divided by lambda b, wavelength for the Balmer series is r into 1 divided by 2 square minus 1 divided by n1 square, where n2 is equal to 3/4 1 up to infinity. By putting n equal to infinity in this equation, we get the series limit of the Balmer series. This is the shortest wavelength. This is for shortest wavelength, and in this case finally we get the answer lambda b is equal to 4 divided by r. But for that Lyman series, 1 divided by lambda l is equal to r into 1 divided by 1 square minus 1 divided by n square. Here n equal to 2, 3, 4, so on up to infinity. By putting n equal to infinity, we obtain the series limit of the Balmer series. This is the correct shortest wavelength of the Lyman series, that is lambda l is equal to 1 divided by r. This is equation number 2. Dividing equation 2 by 1, we get the wavelength of the Balmer series divided by wavelength of the Lyman series. The ratio of the wavelength of the Balmer series to the wavelength of the Lyman series, that is 4 divided by 1. The option A is the right answer. The next question is, if the wavelength of the first line of the Balmer series of hydrogen atom is 6561 angstrom, the wavelength of the second line of the series limit should be. For the Balmer series, n1 equal to 2 and n2 equal to 3. For first line here n2 is equal to 4. This is for second line. This is for first line and this is for second line. Here also n1 equal to 2. This is first line and this is second line. Now the ratio of the wavelength lambda 2 divided by lambda 1 is equal to 1 divided by 2 square minus 1 divided by 4 square whole divided by 1 divided by 2 square minus 1 divided by 3 square. We get the answer 3 by 16 divided by 5 divided by 36, or 3 divided by 16 into 36 divided by 5. Finally, when you are going to calculate, you get the answer 27 divided by 20. 27 divided by 20, or lambda 2 is equal to 20 divided by 27. 20 divided by 27 into lambda 1, that is equal to 20 divided by 27 into lambda 1, that is 6561 angstrom. We get the answer lambda 2 is equal to 4860 angstrom. Option C is the right answer. And the next question is, the radiation corresponding to. The next question is, the energy of an excited state of hydrogen atom is, that is 0.85 electron volt. The energy of an excited state of hydrogen atom is 0.85 electron volt. What will be the quantum number of the orbit if the ground state energy of the hydrogen atom is minus 13.6 electron volt? Energy in the nth orbit is equal to E1 divided by n square. From using this equation, we can calculate the quantum number of that orbit. Therefore, n square is equal to E1 divided by En. Energy in the first orbit, that is 13.6 electron volt. In that nth orbit is minus 0.85 electron volt. N square is equal to 16. Minus 13.6 divided by 0.85, you get n square is equal to 16 and n is equal to 4. The option A is the right answer. And the next question is, the longest wavelength of the Balmer series is 6563 angstrom. The Rydberg constant is, the Rydberg constant for the longest wavelength of Balmer series, n1 equal to 2 and n2 equal to 3. 1 by lambda is equal to r into 1 divided by n1 square minus 1 divided by n2 square. When you are calculating, finally you get the answer 1.09 into 10 to the power of 7 per meter, because it is a constant value. This is 10 to the power of 7 per meter. Option C is the right answer. Next, I would like to solve some other types of questions, that is statement type questions. Here in the first question, Rutherford's nuclear model. Rutherford's nuclear model could not explain. The first statement is, 5 atoms emit light of only discrete wavelengths. The second statement, how could an atom as simple as hydrogen consisting of a single electron and a single proton emit a complex spectrum of specific wavelengths? According to Rutherford atomic model, the whole mass of the atom is concentrated at the center. Whole mass of the atom is concentrated at the center, and most of the space in the atom is empty. The size of the atom is in the order of 10 to the power of minus 10 meter or angstrom, and the size of the nucleus is 10 to the power of minus 15 meter. Nuclear model could not explain why atom emits light of only discrete wavelengths, and it could not explain the hydrogen consisting of a single electron and a single proton emit a complex spectrum and a specific wavelength. Option A, only first statement is correct. Option B, only second statement is correct. Option C, both could not explain. Option C is both the statements are right. Option D, none of these. Here, according to Rutherford nuclear model, could not explain. It could not explain the first statement and second statement. The option C is the right answer. Here, option C is the right answer. And the second question is, Rutherford's, this is alpha particle, Rutherford alpha particle scattering experiment concludes that. What is the conclusion of Rutherford alpha ray scattering experiment? In the first statement, there is a heavy mass at center. Yes, it is right. Electrons are revolving around the nucleus. No. Here, this postulate is explained by Neil Bohr, but this postulate is does not explained by Rutherford. There is a heavy mass at the center. According to Rutherford, whole mass of the atom is concentrated at the center. Most of the space in the atom is empty. Only the statement 1 is the right answer. That's why option A, only the first statement is right answer. And the third question is, the observations of Geiger and Marston experiment are, according to Rutherford alpha ray scattering experiment, what are the observations? Most of the alpha particle, or many of the alpha particles pass straight through the gold foil. Yes, it is right. And only about 0.14% of the alpha particles scattered by more than 1 degree. This is also right. Then the third statement, about 1 in 8,000 of alpha particles is deflected more than 90 degree. This is also right. Very few particles are reflected back. This is also right. Already I have studied the scattering experiment or Rutherford alpha ray scattering experiment, and the alphas was placed in a lead cavity. It emits the certain radiations. That radiations are incident on a gold foil. All that alpha particles are collimated into a single fine beam with the help of slit, and most of the alpha particles fall on the gold foil. They are easily passes through the gold foil. Only about 0.14% of alpha particles are scattered more than 1 degree, and about 1 in 8,000 alpha particles deflected more than 90 degree. Very few particles are reflected back. Here, option D is the right answer. And the next question is the trajectory of an alpha particle. Very few alpha particles are scattered back or reflected back in the trajectory path. A trajectory of an alpha particle in Geiger and Marston experiment is explained by Coulomb's law, second one Newton's law, third one Gauss law, fourth one Faraday's law. Here Coulomb's law, it is applicable for electrostatic force. Suppose if I consider here, this is the positively charged alpha particle. This is the alpha particle, positively charged alpha particle. It is equal to helium atom. And consider another nucleus where the electron is revolving around this nucleus. When these alpha particles are comes to rest before the central core of this atom because due to Coulombian repulsive force. That's why it is explained by using Coulomb's law and Newton's law. F equal to ma, force is equal to mass into acceleration. Every body continues to be a state of rest or in motion unless it can't expelled by the external force. This is also right. But here the trajectory of an alpha particle in a Geiger and Marston experiment is explained by using Gauss law. No. Faraday's laws. No. Here the statement 1 and statement 2, these are the right answer. Here option A, 1 and 2. And the next question is Bohr's atomic model assume that the nucleus is out of infinite mass and is at rest. And the second question is electrons in a quantized orbit will not radiate the energy. Option 3 is, statement 3 is mass of electrons remains constant during revolution. And the fourth statement is emission or absorption of energy results to transition of electron from the orbit to another. Choose the correct option from the codes given below. The option A is only 1 is right. Option B is 1 and 2. Option C is 1, 2 and 3. Option D is 1, 2, 3 and 4. Yes, it is right answer because the nucleus, it is infinite mass and it is at rest. Yes, electrons in a quantized orbit will not radiate the energy. Mass of electrons remains constant during the revolution. Yes, that's why option D is the right answer. And the next question is which of the following statements are true regarding Bohr's model of hydrogen atom? According to the hydrogen atom, for hydrogen atom, according to Bohr's model, orbiting speed of electron decreases as it shifts to discrete orbits away from the nucleus. Yes, and the electron is revolving around the nucleus, its speed is decreases and it shifts to the orbits from lower orbit to higher orbit. And the second statement is radii allowed orbits of electron are proportional to the principal quantum number. Yes, because the R is directly proportional to n square. And third statement is frequency with which electrons orbit and around the nucleus. No, in discrete orbits is inversely proportional to the cube of the principal quantum number. No, it is the square of the principal quantum number. And fourth, binding force with which electron is bound to the nucleus increases as it shifts to outer state. No, here the statement 3 and statement 4 are wrong. Only the statement 1 and statement 2 is right. The option A is the right answer. And now I would like to solve some problems on matching type questions. Here the two columns are given. Now we are going to match with column 1 and column 2. Match the column 1 and column 2. In the column 1 they are given J.J. Thomson, Rutherford, Frank Hertz and Niels Bohr. According to J.J. Thomson, the positive charge is uniformly distributed throughout the atom and negatively charged electrons are embedded in the atom like seeds in a watermelon. It is also called plum pudding model. J.J. Thomson. It is also called plum pudding model. For this J.J. Thomson, A equal to 2. And according to Rutherford, Rutherford explained nuclear model of the atom, and the Niels Bohr explained the existence of discrete energy level in an atom. Frank Hertz explained the existence of discrete energy levels in an atom, and Niels Bohr gave the theory of hydrogen spectrum or explanation of hydrogen spectrum. J.J. Thomson explained or gave the plum pudding model of the atom. Rutherford gave the nuclear model of the atom. Frank Hertz gave the existence of discrete energy levels in an atom, and Niels Bohr gave the theory of hydrogen spectrum or explanation of the hydrogen spectrum. And the second question is, consider Bohr's model to be valid for a hydrogen like atom with atomic number Z. Match quantities given in column 1 to column 2. Now I write the values in column 1 and column 2. In this column 1, here the first one, that is Z cube divided by n to the power of 5. Already all these values are given in your CD materials. B Z square divided by n square. C Z square divided by n cube. D Z divided by n. And column 2, here the angular speed. P magnetic field at center due to revolution of electron. And C potential energy of electron in nth orbit. D frequency of a revolution of electron. This is a given table. Now we are going to match the column 1 to column 2. In the column 1, Z cube divided by n phi. Z cube divided by n pi. Z atomic number, cube of the atomic number divided by their principal quantum number, that is equal to, here this is equal to angular speed according to the Bohr's model of for hydrogen atom. And Z square divided by n square. Z square divided by n square, which is equal to potential energy of an electron in the nth orbit. And Z square divided by n cube, it is equal to, and it is applicable, this formula is applicable or it is used to calculate the magnetic field at the center due to the revolution of electron. And Z divided by n, it is equal to frequency of an revolution of electron. And now I would like to solve some assertion and reason type questions. Already you know how to solve these kinds of problems. Once again I will explain the directions. Each of these kinds of questions contain two statements, assertion and reason, or statement 1 and statement 2. Each of these questions also has 4 alternative choices, only one of which is the correct answer. You have to select one of the codes A, B, C and D. Suppose the option A is the right answer, it gives the meaning assertion is correct. Assertion is correct. reason is correct, and reason is a correct explanation for assertion. If the answer B is right, in that case assertion is correct, reason is correct. Reason is not a correct explanation for assertion. If the answer C is right, assertion is correct, reason is incorrect. If the answer D is right, in this case assertion is incorrect, reason is correct. Now we will see the first question. Assertion. The force of repulsion between atomic nucleus and the force of repulsion between atomic nucleus and alpha particle varies with the distance according to inverse square law. Yes, assertion is correct. The force of repulsion between atomic nucleus and alpha particle varies with distance according to inverse square law. That's why it obeys or it explains Newton's law and Coulomb's law. Reason. Rutherford did alpha particle scattering experiment. In this case, both assertion and reason are the true, but reason is not correct explanation for assertion. That's why here the option B is the right answer. Assertion is correct, reason is correct, reason is not a correct explanation for assertion. The next question is, electrons in the atom are held due to Coulomb forces. Held due to Coulomb forces. Reason. The atom is stable. The atom is stable only because the centripetal force due to Coulomb's law is balanced by the centrifugal force. In this case, the assertion is right, reason is wrong. Electrons in the atom are held due to the Coulomb forces. Yes, it is right. But the atom is stable only because the centripetal force, according to the Bohr's postulates, electrons revolve around the nucleus in a fixed orbit of definite radii. As long as the electron in a certain orbit, it does not radiate any energy. The assertion is right, reason is incorrect. And the assertion is right, the reason is incorrect. The option C is the right answer. And the next question is, hydrogen atom consists only one electron. Hydrogen atom consists only one electron, but its emission spectrum has many lines. Yes, assertion is right. Reason. Only Lyman series is found in the absorption spectrum of hydrogen atom, whereas in the emission spectrum all the series are found. Yes, both are right, but the reason is not correct explanation of assertion, because when the atom gets appropriate energy from outside, then this electron rises to some higher energy level. Now it can return either directly to the lower energy level or come to the lower energy level after passing through other energy levels. All these possible transition takes place in the source, and many lines are seen in that spectrum. Both are true, but the reason is not correct explanation of the assertion. Then the option A is the right answer. Then the next question is statement 1 and statement 2. Between any two given energy levels, the number of absorption transition is always less than the number of emission transition. Yes, it is right. Statement 2. Absorption transition start from lowest energy level only. It is also right, because when we draw the energy level diagram, here in this case n equal to 1 and here n equal to 2, and the absorption transition starts from lowest energy level only and may end at highest energy level. But the emission transition may start from higher energy level and end at lower energy level. Both are true. Reason is the correct explanation of the assertion and statement 2 is the correct explanation of statement 1, because between any two given energy levels the number of absorption transition is always less than the number of emission transition. In this case, option A is the right answer. Statement 1 is right, statement 2 is right, statement 2 is the correct explanation of the statement 1, or assertion is right, reason is right, and reason is the correct explanation of the assertion, then the option A is the